Hey guys, welcome again to the Maths Club. I'm going to continue our series on logarithm, and today we'll be looking at how we can use the logarithm table. So I'm sure everybody has actually seen the logarithm table, but if you have not, let me show you a sample. So this is the logarithm table. You can see it at the back of your maybe new general mathematics or any maths textbook that you use, or you have a 4 figures table, you will see it inside. So this is the logarithm table that we're going to be looking at. How are we going to read? Yes, I'm sure you've seen all these values here. How can we be able to pick out the value that we need? So logarithm, before we begin, there are some things that we should know. I think I've mentioned this before, that if you have a logarithm to base 10, that logarithm is known as the common logarithm. And I also said it before in one of the previous videos that if you have a log that the base is not given, you can assume that the base is in base 10. Great. So in the log of any number, there are two parts. Let's take for instance, this is the value that we get when we check the logarithm table. So we have 5.6785. This first part is the integer part of the logarithm, known as the characteristics, and the other part is the decimal part. This 0.6785 is a decimal fraction, right, known as the mantissa. Right, so the whole number part is known as the characteristics and the decimal part is known as the mantissa. To read from the logarithm table, I have to first convert the number to standard form. After I convert the number to standard form, I'll find the logarithm of the number portion and express it in the power of 10. Then I will add both powers and then I will get my results after adding the powers. So let's look at some examples that would actually bring home these steps that we've talked about. So the first example is saying that we should find the log of the following numbers. So this number is 69.23. So to find the log of 69.23, I'll first write that 69.23 in standard form. And that will be, I'll move this one back. So this will be 6.923 times 10 raised to the power of 1, because I moved this one time. Then the next step said that we should find the logarithm of the number portion, right? And this is the number portion, right? So 6.923. Let's see how we're going to look for it in the logarithm table. So this is my logarithm table. First thing, you want to ensure that the heading is saying logarithm. Now you can see the heading, the first number that I have here is 10, but I'm trying to find something that is 6.923. So that means that I won't be able to find 6. What we do is that we join these first two numbers, which is 69. We join the first two numbers, 69, then we go to the logarithm table and then we look for the colon. Under this place, look for number 69. Number 69. Here it is, right? Now, so that means that this is the line that we're interested in. If you notice something, there are numbers here 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. What does that mean? Because 69 under 0 is different from 69 under 1, different from 69 under 9. So we need to go to our table and say, after the first two numbers, the next number is number 2. So that means that we'll go to 69 under 2. So this is 69, this is 0, this is 1, this is, so the number that we need there is 8401. So let's put it down. 8401. But it does not end there. It does not end there. We still have another number there, number 3. Right? How are we going to put in the number 3? If you go to our logarithm table, you see another place called the mean difference. You can see that there are other numbers here too. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we said the first number is 69 under, I think that was under 2, right? Then we'll now come to this mean difference. The last number here, which is 3, is what I will look for in the mean difference. So 69. So I will come here. This is for 1, this is for 2, this is for 3. Under 3, the value that I have here is what? Number 2. So I'll come here and add that 2 to the previous thing I had. 2 plus 1 is 3, so 0, 4, 8, right? So the value that we got when we found the logarithm table from logarithm table is 8403. But let me also say something, that the logarithm table, the values in the logarithm table are actually in decimals. So this is 0.8403. They might not show it at the top, but all these values here is 0.7404, 0.0. So now that we've gotten the value of 69 under 2 difference 3, right? 69 under 2 and difference 3. We've added those two numbers. the next thing to do is we said we should express that logarithm in power of 10. So I'll come here and say this 69.23, I can replace that as 10 raised to the power of 0.8403 times 10 raised to the power of 1, right? And then from the law of indices that we know, it's the same base and the multiplication that is joining them, so we can add the power. So that will be 10 raised to the power of 0.8403 plus 1, right? And if I had, that would be 10 raised to the power of 1.8403. So we're saying 69.23, the log of 69.23 is always going to be the power. Do you get? It's going to be the power. So how is it going to be the power? So that means the answer is 1.8403. If you remember what we said about logarithm, so this is one of the old slides that we used in one of the previous videos when we were introducing logarithm. We said the logarithm answers one question, that how many of one number would I multiply together to make another number? Well, we said for us to find 6 to 5, we have to raise this 5 up to a power of 4. That means 5 times 5 times 5 times 5, right? That will give me 6 to 5. Remember, the logarithm of a number x to a given base b is the exponent to which the base must be raised to obtain x. Given this definition of logarithm, let's now compare it to what we have here. Now, we're trying to find the log of 69.23. You know, I said something that if you're just giving log 69.3, we can assume that the base is 10 because that is a common logarithm, right? So for us to actually find 69.23, right, the base is base 10. We agree with that. We have to raise base 10 to 1.8403. And that was why we said our answer is 1.8403. Let's check it out in the calculator and see what we're going to have when we raise 10 to the power of 1.8403. So we have a calculator. So if I say 10 raised to the power of 1.8403. So you can see we have 69.23. And that is why our value for this log is 1.8403. Because for us to find 69.23 with base 10, we have to raise that base 10 to 1.8403. So this is really the breakdown of the solution. Yeah, so this is correct. So this next question is saying 7033, meaning what will I raise to the power of 10 that will give me 7033? So 7033. The first thing is that we convert it to standard form, and that is 7.033 times 10 raised to the power of 3. Then the next thing is we find the logarithm of, if you look at it, this is 70. We can't find 7, so 70 under 3 difference 3. So let's go to our logarithm table and look for it together. So 70, this is 0, so 70, let me put this, 70, 0, 1, 2, 3, that is 8470. So this is 8470. You can say 0.8470. 70 under 3, then difference 3. If I go to difference 3 is 2. So I'll just add 2 to this, and that'll give me 0.8472. Right, so like I said, whatever value you have, you raise it, so 10 raised to the power of 0.8472 times 10 raised to the power of 3. Now, because of the law of indices, we can now add the powers and say 0.8472 plus 3, right? And that will give me 10 raised to the power of 3.8472. So it's telling me that if I raise 10 to the power of 3.8472, I would have 7033. Let's see if this is true. So this is 10. I'm raising it to the power of 3.8472. Great. You can see we have 7033. It might not be the exact value because of approximation, all of those things, but you get something really close. Great. So our answer is 3.8472. Let's see if we're correct. Great. So 3.8471. Maybe due to some four-figure table might give you more accurate values than other ones, but it's fine. The next value is 4.911. So let's see. 4.911. Of course, this value is already between 0 and 10, and it's less than 10. So you cannot say 4.911. You can say times 10 raised to the power of 0, because 10 raised to the power of 0 is still 1, right? So we will go to 49 under 1 difference 1. Let's go to our logarithm table. So this is 49. I think the first value is 0. Okay, so 49, this is 0, this is 1, so this is 6911, right? 49 under 1 difference 1. Difference 1 is also 1, so that is 6912 if I had both of them. So that is, I can say 10 raised to the power of 0.6912 times 10 raised to the power of 0, right? By the time I have both of them together, I will say I have 10 raised to the power of 0.6912. So that means that the log of 4.911 is just what? 0.6912. So we can actually now check if our answer is correct. Yeah, 0.6912. Great. Now the next question is now saying that we should find the log of 0.003512. So 0.003512. So let's come back to standard form first. That will be 123. 3.512 times 10 raised to the power of minus 3, right? Now we check 35 under 1 difference 2. So let's go to our logarithm. We have to ensure that it's logarithm that we are seeing here. 35 under 1. So this 1 difference 2. Difference 2 is value 2. So that will be 5453 plus 2. 5455. So this will be 10 raised to the power of 0.5455 times 10 raised to the power of minus 3. Then we can add the powers, right? And this will be 0.5455 plus minus 3. But in logarithm, there is something that is very, very interesting that we have to do. We have to maintain the integrity of this minus 3. If I do 0.5455 plus minus 3, I'll be having minus 2 point something. But if I do it that way, when I want to, so Antilog is like going from the logarithm back to the number. When I want to do the Antilog, the value that I will get would not be correct. So in logarithm like this, they don't do that addition when you have a minus 3. So whenever you're doing a number less than 1, you have to be very careful, right? So what do? They just say the log of 0.003512 is equal to what? Just the top. This is 0.5455 minus or plus minus 3, right? After they now do this, what did they do? So you can write and say minus 3, put the minus 3 at first, plus 0.5455. What did they do? They just say something that this minus 3, they're going to represent it as what? As bar 3. So bar 3 points, then the remainder of this guy, which is 5455. That way, if anybody is walking back and wants to get the original number that this log was gotten from, right? When the person says bar 3, it means that there will be 3 zeros, 0.00 before the conversion, right? But if I had done this plus something, I will have had minus 2, right? And that will mean 2 zeros. So you can see that is not the same value. So because of that particular thing, we don't add, right? We use a bar notation. And let me just say, you know that this bar 3 is not, this is not the same thing as saying minus 3.5455. No, it is not the same thing. This one is saying minus 3 plus 0.5455. If you add this guy, you are going to have something entirely different. So you must know the distinction, right? So the take home is that whenever you have a number less than 0 and you have a minus 3, don't do minus 3 plus, just say bar 3, then dots, whatever is after it, right? 5455. So that being said, this is our answer. Our answer is bar 3.5455. Let's see if we are correct. Great. Now the next question is saying that we should find the log of 0.5623. So 0.5623 convert to standard form. That will be 5.623 times 10 raised to the power of minus 1, right? So we'll find 56 under 2 difference 3 in the logarithm table. So let's go to the logarithm table. 56 under 2 difference 3. right? So this is 7497. Difference 3 is 2. So 7497 plus 2, that is 7499, right? So this is 10 raised to the power of 0.7499 times 10 raised to the power of minus 1, right? So what am I going to do? I will add both powers. I said 10 raised to the power of 0.7499 plus minus 1, right? So like I said before, the log of 0.5623 is minus 1 plus 0.7499, and the way to write this is by saying bar 1.7499, right? Because this bar 1 will symbolize that if I have any chance to convert it back to the original number, there was only 1 0 before the value, which is consistent with what we have. Yes, so we have bar 1.7500, but if you look at it, about 1.7499. If I had converted it to 2 decimal places, that would be 7500, right? So it's very, very close, and that is the answer for this. So that is it about finding the logarithm of a particular number in the logarithm table, right? So you express in standard form, look for the whole number part in the logarithm table, express that number as a power of 10, add the powers. The summation of the powers is your logarithm, and we saw why the summation of the powers is our logarithm based on our definition of logarithm. So in the next phase, we're going to be looking at, we have the logarithm now, right? We want to get back our number, our initial number. We want to get back our initial number. How do we do that? We use the anti-log table, anti like the reverse log table. So let's go into it using the anti-log table. And of course, I'm going to use examples to solve this. So we have one example that has babies. The example is saying find the anti-log of the following numbers. So we have the log as 1.8403. So we have the log. We want to find the anti-log, which is the number that gave us this 1.8403 in the logarithm table. So 1.8403. This first step is that break this 1.8403 to its components in terms of powers of 10. What do I mean? This is 1 point, so this will be times 10 raised to the power of 1. Where is this 1 coming from? The whole number part. So this will also be 10 raised to the power of the remainder, which is 0.8403. So if you look at what we did, this is very similar to what we're doing here. Let me move to the previous example on this. Great. When we add 6.923, we found 69 under 2 difference 3 in the logarithm table. Then we had the value to be 0.8403. We said 10 raised to the power of 0.8403 times 10 raised to the power of 1, right? And then we added. So what we were just doing now is this 1.8403, we are breaking it back into this 10 raised to the power of 0.8403 times 10 raised to the power of 1. So we're just breaking it back here. Now that being said, we now have to go to the anti-log table to find what this would give us. So if you go to the anti-log table, you ensure that at the top what you are seeing here is the anti-logarithm. So we had 0.8403. So I'll go to 84 under 0 difference 3. So 84 or 0.84, you can see there's 0.84 under 0 difference 3. So we have 6918 plus 5. 6918 plus 5, that will be 6923, right? So this is 6923 times 10 raised to the power of 1. One thing you need to recognize is that any value you take from the anti-log table, there is a point after the first value, right? So this is not 6923, this is 6.923, right? Just like in the logarithm table, if you see 8403, you know that there will be a point before the 8403. That's why we had 0.8403. But in the anti-log table, when you have 6923, there will be a point after the first value. Now 10 raised to the power of 1 is something as saying times 10. So this is like saying 6.923 times 10. And if I multiply this will give me what? 69.23. So we are back to our initial value. If you go back and you see that this was 69.23, gave us 1.8403 when we did the logarithm. Great. And if we use a calculator, if you say 10, so you can take a calculator and you say 10 raised to the power of 1.8403, you see your answer there. So when you say 10 raised to the power of 1.8403, you will see your answer to be 69.23. That's how you can also find if your value is actually correct. So let's see this other example. Let's see what first correct. Great. This is 3.8471. So we're going to break it. 3.8471. So first we break it into two component parts. 10 raised to the power of 0.8471 times 10 raised to the power of 3. Right? So we're going to go to 0.84 under 7 difference 1 on our Antilog table. 0.84 under 7 is 0, 1, 2, 3, 4, 5, 6, 7, and difference what? Difference 1. That's 7031 plus 2, which is 7033. Right? We know that would be 7.033 times 10 to the power of 3 is 1000. So by the time you multiply this by 1000, what do you have? You have 7033. Let's see if our answer is correct. Great. This example is saying 0.6912. You might want to pause the video and try it out yourself. Welcome back. Let's solve it together. 0.6912 expressed in powers of 10. So that's 10 raised to the power of, 0.6912. I could say times 10 raised to the power of 0, but that is not necessary. So what will I go? I'll go to 0.69 under 1 difference 2. Let's go there. 0.69, this is 0 under 1 and difference 2. Difference 2 is value 2. So that is 4909 plus 2. And that will give me 4911. Right. So this will give me 4911. Of course, there is a point after the first 4. So that's 4.911. Let's see if our answer is correct. Great. Great. If you got it, well done. Next question, we have about 3.5455. Can also pause the video and try it out yourself. Welcome back. So we had about 3.5455. So I could break this down and say this is 10 raised to the power of 0.5455. I remember what we did. We said about 3 seems as saying minus 3. So 10 raised to the power of minus 3. So let's find 0.54 under 5 difference 5. 0.54 under 5 with a difference of 5. The difference of 5 is 4. So this is 3508 plus 4, which is 3512. 3.512 times 10 raised to the power of minus 3. So I'll just shift this 1, 2, 3 times, and that'll be meaning that I'll have 3 zeros before my 3512. So this 0.003512. Great. So this should be our answer from this. Let's see if we're correct. Great. And the last example is bar 1.7500. So bar 1.7500. This is 10 raised to the power of 0.7500 times 10 raised to the power of minus 1. So we're going to look for 0.75 under 0 difference 0. 0.75 under 0, that is 5623, but there's no difference of 0. The first difference is 1. So our answer will just be 5.623 from here. So this is 5.623 times 10 raised to the power of minus 1. By the time I multiply this by 10 raised to the power of minus 1, I'll just move. That means there should be only 1 0 before my 5623, and that will be 0.5623. Let's see if we're correct. Great, we're correct. And with that, we've actually seen how to use the logarithm table to find the log of any value, and how to do a reverse. Right, I have a log, I want to find the value that gave me that log. I'll have to use the Antilog table, and we have seen how we can be able to break it and find our answer. In the next video, we'll be looking at how to do common multiplication, maybe multiplication and division using logarithm. See you in the next video.